So today I wanted to talk to you about planetary analogues and their importance in planetary research and especially in astrobiology. So as you heard from the introduction, I'm interested in this field analogues, but also doing some lab works and space experiments. But today I will focus on the things that we do on Earth on these field sites and in these extreme environments. And for that, I will show you some examples of works we have been doing in the past almost 10 years in different locations on Earth, where I had the chance to participate in and join some research projects on testing for habitability and biosignature detection. So first of all, planetary field analogues are very important, of course, to planetary science in general, to learn about planetary processes, both for geology and biology on Earth and elsewhere, to test protocols and strategies, methodologies, operation technologies, and payload instrumentation. This is because, of course, space missions to planetary bodies in our solar system are very expensive, very time-consuming, taking decades to reach their targets. So it is crucial for scientists, engineers to test all these strategies, methodologies, and new instruments and technologies on similar analog environments. But also in the meantime, we can prepare these space missions and also training highly qualified personnel, as well as science and operation teams. We can also engage the public, the space agencies, and the media in knowing more about our Earth, but also what else is out there. And for the case of astrobiology, of course, that helps us to define detectable biosignatures from all the life forms that we have on Earth and to define the limits of life and habitability from Earth. So you can see here a few examples of field sites, collections from a very nice review from Dieter Martins and colleagues, for example, or specifically for Antarctica, one of the harshest continent on our planet, where you have lots of different fields that can be analogues to many locations of our solar system, and also a nice review from colleagues, Alessia Casaro and colleagues published a few years ago. So it's true that we also go there to appreciate the beauty and the diversity of the natural environment of our own planet. And sometimes it feels like we are really exploring distant worlds. Here, for instance, in the Atacama, you just need to take out the blue out of the sky, and it feels like you are on Mars. So if we go back to the question mainly about habitability and extreme environments, if we look at the evolution of life on Earth, we think that life started very soon after the conditions became hospitable on our planet, meaning after the last phase of the late heavy bombardment, so around 4 billion years ago. And but of course, it is very challenging to find traces of life from this era because of plate tectonics. Many of the rock records have been put back into the mantle and destroyed, and so we have a very few fossil records from these dates. But earliest traces of life are still debated, but date back to 3.5 billion years ago, with an origin around 4 billion or 3.8 billion years ago on our planet. So I'm telling you this because this illustrates how life also evolved with our planet and adapted and to colonize lots of different environments. It is important to note here that for most of the time life was mainly prokaryotic, so only archaea and bacteria, and then became eukaryotic, and multicellular life appeared very late for our evolution of the planet. So that's something we can take into account also when we look for life elsewhere. We are not expecting to find plants or animals on Mars, but mainly microbes. So as I said, all this evolution of life on Earth, life adapted to colonize all habitable environments on our planet, even changing global and local conditions, with, for instance, the rise of photosynthesis, here noted at 3.2 billion years ago, that of course gave rise to oxygen in the atmosphere and changed also completely the planet in its the planetary conditions, or at least on Earth. Yeah. So nowadays, as I said, there are very few places that are devoted of life on our planet. And in the last decades, we found out adaptation strategies for microorganisms to live under very extreme conditions for us, but they are adapted to these, from the dry valleys in Antarctica in the top left to hydrothermal deep vents, of course, in the deep sea, or you see the Yellowstone hot springs, or very salty conditions in salt crust, or even adapted to high radiation environments. And this allows us to define our terrestrial zoo, so that define the limits of life as we know it in terms of physico-chemical conditions. And we named all the organisms living under such conditions extremophiles, because they are adapted to these particular conditions that are outside of our range of conditions for humans, at least, and most of the life that we know from Earth. And they have been named after their main resistance. For instance, halophiles, they love salts. Barophiles, they like high pressures. Radiophiles, they like radiation. Thermophiles, they like high temperature, etc. And so we can study these places, these extreme places on Earth, to learn about the limits and draw a map of the habitable conditions of terrestrial life, because that's the only example of life that we know, of course, for now. And so these are the limits, the current limits. That may be a bit outdated. There are always new organisms that have been found, that are found today. And so it is important to note here that the limits of life in terms of actively growing, meaning that they are metabolically active under these conditions. So we have microbes that can grow at temperatures higher than 120 degrees, or they can grow at minus 20 degrees, etc. So the scales for survival, so that's the other parts. Survival can go much beyond these limits of life here, as we have organisms that can survive under space conditions, etc. But they are just entering dormancy, and they are just waiting for the conditions to be good again to grow. So all of this allowed us to realize that life on Earth, thanks to all these 4 billion years of evolution, has been able to colonize and live under all conditions, that physico-chemical conditions that we find on our planet. And so that's how Dr. Malcolm said that life always finds a way. So that allows us to look at, of course, other places in our solar system, at least, and to imagine what are the potential habitable environments under the different planets and moons of our solar system. And we can draw hypotheses based on these defined limits. And so for now, the main candidates, of course, to find active life outside of the Earth are still Mars and the icy moons of Jupiter and Saturn, Europa and Enceladus. So as we saw that life on Earth could potentially can live under very high pressures in subsurface oceans, there are potential places like that on Europa and Enceladus, or life forms on Earth are adapted to very salty conditions, and we do have salts on Mars and brines. So we can do all these hypotheses to look for these habitable conditions elsewhere. And this is one of the main goals of current missions to Mars, but also to the icy moons. So for this talk, I will mainly focus on Mars, but it also applies to a current mission to the icy moons, at least for Jupiter. And so rovers to Mars today are looking at past habitable conditions and potential traces of life. For instance, the Perseverance, the Mars 2020 rover, actually carrying instruments together with the future ExoMars Rosalind Franklin rover. So they are carrying instruments that are potentially able to detect traces of life. And of course, the Mars 2020 rover is preparing for the Mars sample return, with its main goal of collecting samples that will brought back to Earth in the futures for characterization in our labs. But so the instruments that you see here, so we use some of them, of course, in the field, and that's one of the goal of using field analogues experiments and field analog studies. And especially interesting for my part of the research are spectroscopy-based instruments that have the potential to detect molecules and biomolecules, so traces of life, without disturbing the samples. And the combination of different spectroscopy techniques can give us clues about the molecular and elemental compositions of the samples. So, of course, the dream of every astrobiologist would be to have the tricorder instrument from Spock and data, and then to have in a few clicks to be able to characterize life forms on an unknown planet. But we are not there yet. But we have some, as I said, some techniques that can go in this direction, and some different spectroscopy techniques, for instance, to bring us a step closer. So, for instance, coupling LIBS for laser-induced breakdown spectroscopy with which is looking at the elemental composition of the samples by focusing a laser and ablighting and producing a plasma and looking at atomic transition emissions. So you have information about the elemental composition. And if you couple that with Raman spectroscopy and visible near-infrared spectroscopies, which are looking at the molecular structure, you have a very nice complementary information about your samples. And so you can characterize, of course, minerals. That's what the rovers are doing on Mars today, but also you have the potential to look at molecular structures and so identify molecules and potential biomolecules. So this combination is what we are actually doing in the field with colleagues here from DLR with portable instruments, and so we are mimicking what a rover would do on Mars, for instance, but that can be applied to other planets, and so to help look at at the protocols of data collection, but also data processing, and using these kind of techniques. So from my side, I mainly work with Raman spectroscopy. So it's still quite a new technique for planetary science. There are two Raman instruments on Mars 2020, one that is on the Rosalind Franklin rover and one for also the MMX mission. So there are not a lot of instruments. So that was the goal, to understand what are the detection potential, the detection limits, and the potential for such technique to be used in planetary exploration. And especially interesting is comparing portable instruments that are more or less in the same range as instruments carried by the rovers to laboratory instruments to further infer about the detection limits and adapt protocol for acquisition. So Raman spectroscopy has been extensively used for mineralogy, but as I said, it has also the potential to detect traces of active or past life. Mainly, it can detect a vast range of organics, and for fossil life, pigments are especially interesting thanks to their high preservation potential in the fossil record. So now I will show you a few examples of field studies I had the chance to participate in some of these planetary analog environments. And I will start with Mars and in the Atacama Desert. So for that, I joined the group of Dirk Schulze-Macour from the TU Berlin, and the project looking at the dry limits of life in the Atacama Desert, called the habitability of Martian environments. And this was very interesting for the analogy to Mars, as hygroscopic salts, so salts that can capture water from the water vapor from the atmosphere, are considered on Earth the last outposts of life. So they are the dry limits of life. And so there are organisms that use the deliquescence. You know, if you leave your table salt under humid condition, it will attract water and be clunked together. So that's the deliquescence. And so under these environments where it never rains, the microbes can grow inside the salts and use only this deliquescence to use only the water vapor, but not the rain water. And so we believe that's what could have happened also if life originated on Mars. We still don't know, but that's a hypothesis. If life originated on Mars under wetter condition in the past, it could have adapted to drier and drier conditions as the planet evolved and lost its atmosphere and surface water. So life could still find some outposts under salt crusts and on the surface of Mars. So on Earth, we have, of course, sodium chloride, but we have also lots of different salts that have different potential, hygroscopic potential. And on Mars, especially interesting are fluorates and perchlorates, which have a much higher hygroscopic potential, so that can form liquid brines on the surface of Mars in certain conditions, even today. So that can still be a potential source of water for Martian organisms. So as you can see in this salt crust and nodules, you can find the colored bands in the inside of these nodules that are indicating of the colonization of photosynthetic organisms. And in these, I was especially looking at the distribution of Raman signatures to look at the habitability of the nodules and the detectability of these traces of life. So just a few impressions from the field. It's quite an extreme environment for humans, of course, to be in the hot deserts of the Atacama, and especially with no shade and of course no water around. But you see in the bottom right that there is a bit of fog that comes once in a while. So that's the water vapor that can be used by the organisms. And so here, just to show you that the temperatures can vary quite extremely during the day from 0 to 45 degrees. And the same for the relative humidity, almost 0 to 80%. So that's what the organisms are using. So in the last campaigns, we selected a few areas containing these salt nodules from different salars and from different aridity conditions. And we performed in situ measurements, but also back in the lab, we were able to cut and polish and do some lab measurements on these nodules. And here I was especially interested in looking at the distribution of Raman signal from these nodules. So you can see the main signals from the pigments, as I showed you before. So from carotenoids and chitonemine, these are pigments associated with photosynthetic organisms, but are also present in lots of different organisms. And so we were looking at their distribution in these nodules to infer the potential for detectability under very arid conditions. And so we were able to detect them in all the conditions using our portable instruments, but also our lab instruments. So after very dry conditions, I had the chance also last year to join a research project aimed at studying hot environments in the sub-Antarctic regions. So that was led by that is still led by French laboratories and the French Polar Institute. And for that, we went to the Kerguelen Islands, you see in the middle of the South Indian Ocean. And so these islands are volcanic and contain hot springs area and hydrothermal springs. And of course, they are very geographically isolated, as you can see. And so there are very few studies that have been done on the microbial communities in these areas. So the main goal of the project was is to document the microbial diversity and to fill the gap of knowledge on this microbial diversity, but also has a high astrobiological potential since one of the hypothetical places for the origin of life on Earth could resemble the hot springs and hot ponds, such as the ones we found in these environments. Indeed, as you can see on the tree of life on the top right, the oldest branches of life are thermophilic organisms and point towards a mesophilic origin. So that's still a hypothesis, but that could be one of the environments for the origin of life on Earth. And there are, of course, hot springs and geothermal springs are also excellent analogues. So as for the early Earth, but also for the early Mars, as we know that Mars was a very active volcanic planet and had surface water and potential lots of hydrothermal activity as well. So the Kerguelen Islands are all unique also in terms of geology, as the hotspots you can see in the bottom right, separated from Antarctica and India around 150 million years ago, and it is one of the largest large igneous province also on Earth. So as you can imagine, it would be almost impossible to go there and work in these inhabited places without the logistical support of polar institutes like the IPEF, the French Polar Institutes for the TAFs and for Antarctica. And so that's how we arrived by boat in these places, and we were taken by helicopter to arrive in our field sites. And just some impressions. You can see it resembles a bit Chile or New Zealand, where you have these glaciers at sea level, even though the latitude is 40 degrees south, so it's not very high. It's like we are even higher here in Berlin, for example. But because we are in the circumpolar currents in the south hemisphere, the conditions can change very drastically. And you can see a few years earlier, it was the same in the middle of the summer, and then it was completely snowy. So the conditions can be quite tough to sample under under these environments. So yeah, we were able to do that thanks to the Polar Institute, and you see all the fumaroles here that are coming out of the different places, and they have lots of different conditions, physical-chemical conditions themselves. So there are lots of different springs that come out carrying different minerals as well. We put a time-lapse camera to last year, and so that will be recovered hopefully next year. And so yeah, we were able to look at lots of different springs there that can act like natural bioreactors, where you have all these fluids that come from that are heated up in the interior, and that can carry lots of different minerals, and lots of microbial communities are living under this condition in terms of some anaerobic microbes and aerobic microbes, so with or without oxygen. So unfortunately, it was quite tough to do in situ measurements under these conditions with 100 kilometers an hour wind and very wet conditions in the South Indian Ocean. So we were mainly able to collect some samples, and I was doing some measurements back in the main base. You can see with a nice view on juvenile seals in the window there. But still with in situ portable Raman, we were able to characterize a few minerals and some pigments from these areas. And then we continued, of course, the work back in Berlin with the help of some students, where we were able to look at more of the mineral matrix that are the minerals that are present in these settings, and some potential organics and pigments, again, carotenoids, because there are some photosynthetic organisms that are mixed together. And so all of this will complement, of course, the analysis performed by the different groups, and especially the metagenomics that have been going on in the PhD thesis of the colleague in Brest. So that will help to identify new taxa and species carrying these pigments, and potentially enlarge our database of potential biosignature or pigments from extreme environments. So we sampled 4 main sites on the Kerguelen Islands, you see here. So not always in tents, but also using these small cabins that have been put out for many years by the Polar Institute. And new mission is foreseen this year for doubling the sampling and recover in situ measurements, temperatures, and pictures. So of course, the main inhabitants of such islands are not humans, and even though they walk upright, we made sure not to disturb them. So you can hear a little bit, maybe hear the sound they make. So that's, of course, we have to take care of the protection and the biodiversity, which is all of these islands are national reserves for France, and so they are very protected in terms of the impact that we have to minimize for these sanctuaries, for these birds and mammals and plants and everything. And yeah, so just to show you that it's quite a tough journey if you suffer from seasickness, as we had to endure 30-degree inclinations for 8 days to come back from these islands. So nothing to envy to Space Mountain or roller coasters, but yeah. So coming a bit more closer to Europe, at least, and much easier to travel to are the another field site that we used since almost 10 years now, and that is coupled with a summer school actually, and so that is in Vulcano, so Vulcano Island, north of Sicily, part of the Aeolian Islands. You may know Stromboli and others. And this has been so the focus of German research programs, different programs throughout the years, and always coupled with summer school activities. And since last year, we transformed it into the Petras Summer School that was co-organized by us from the LR, but also by the University of Perugia, Uni-Freiburg, IU. The EAI was a big supporter of this first edition of Petras, and will continue to support it. So thanks also to the EAI for that. And so what can we do in Vulcano? So Vulcano offers an easy access compared to the other field site I showed you for logistics, but it is also an excellent Moon and Mars analog for many disciplines with varied geomorphic terrains and magmatic terrains. It has also active volcanisms and fumarole fields it has a lot of different lava fields with different compositions and ash deposits and altered magmatic rocks. So it has been used by different groups to test new technologies from drones to rovers to camera systems, but also volcanologists, geologists, geophysicists, and astrobiologists. And especially that's where we did our main field studies, where we do our combination of the different spectroscopy techniques, as I showed you before, LIBS, Raman, and visible near infrared. And these three in particular provide excellent complementary information. So to understand more the composition of the rocks, but also the molecular structures of minerals and biomolecules, and to train what the rovers are actually looking at on Mars and the future missions. So just a few examples of some of the past and ongoing studies that we performed using these techniques. So here we looked specifically the group of Christine Ramankamp and Susanne Schroeder at DLR look at LIBS data to characterize colored ash deposits in order to optimize data acquisition and processing. And so that was the challenge, using portable instruments to acquire always the good data set and to be able to compare them with different techniques. And so we followed up, of course, using visible near infrared and to further characterize and complement the information from the LIBS. And also visible near infrared is vastly used in space exploration, mainly from orbit. And so this is also nice to provide ground truth for such measurements using portable instruments and then taking samples back to the lab. So for Raman as well, because it complements very well visible and near infrared, especially since some minerals or molecules can be active in one technique or in the other. So it's good to have both. And again, for the astrobiology potential, pigments are mainly detected with Raman and can provide a good biosignature. So we will go back this year to Vulcano, and so yeah, the website is there if you want, and we will open a registration soon for the summer school. So yeah, stay tuned and look at the website if you want. Yeah. And the last project I wanted to mention was looking at lava tubes. So these are very interesting settings on Earth, at least, but also we know that there are lava tubes on Mars or also on the Moon, as we can see them from orbit, and they could represent an excellent shelter for life, as the conditions on the surface of Mars, for instance, became harsher through Mars history, as we saw. So if life started on the surface and then could have adapted to go into a bit deeper in the subsurface and to take shelter from the radiation and the absence of water, etc., inside these lava tubes. So on Earth, these are also very interesting environments because they start completely sterile. So as I said, there are very few environments that are devoted on life on our planet, but of course, nothing can grow and can live in liquid lava. So when the lava cools down, it creates an environment that starts completely sterile, but then become colonized by quite a unique diversity of microorganisms. And for that, we went to two volcanic sets of islands, so the Azores and Iceland. So that's also not bad places to go for. And you can see here we used a multidisciplinary also approach with colleagues from different disciplines to look at the geology, the geochemistry, the biology, and also the spectroscopy of these environments. And you can see here some of the sampling and measurements we did in the field. For example, here we had a portable XRF, so X-ray fluorescence instrument, to look at the elemental composition of the basalts and the lavas. And here you see also the colonized walls with different colors, so all the biofilms that are growing in these beautiful environments. And yeah, we published a study already 3 years ago, and for that we focused on these blue deposits from copper-rich minerals. And yeah, just a few highlights of the study. So here in this, we did some metagenomics approaches to look at the distribution of organisms in these biofilms. And not very surprising, but we found some copper-resistant oligotrophs. So they are organisms known for their high metal tolerance and ability to live and to survive in low nutrients environments, as these lava tubes don't have lots of nutrients to offer to life. And so this could represent a nice analog for putative Martian life, so something that can live under very low nutrients and with a high metal resistance. So that's some characteristics that could be important for Mars. And again, in these settings, with the Raman studies I performed after on the samples, they show the presence of carotenoids. So there's these pigments. They are not only found in photosynthetic organisms, but they can play lots of different roles in life forms, from the 3 domains of life to stabilize membranes, or played an evolution also in the early evolution of life. And they can stabilize also and help against UV radiation. And so these are promising molecules to look out for in other settings on Mars, but also other planets, because they have a very high preservation potential. They are quite easy to detect, at least with Raman spectroscopy. And as I said, they are present in lots of different life forms and many extremophiles, so things that can resemble potential habitats elsewhere. So in summary, I hope I showed you that yeah, field analogues are essential for planetary exploration, to push the limits of habitability and to guide our search for life with new technologies and biosignature models. These extreme environments on Earth are also unique reservoirs of biodiversity, of functions and innovations. So they are key to understand the primitive life forms on Earth and elsewhere, but also that can be used for biotechnology. And so for now, the search for life in our solar system is focused on Mars, and the icy moons are very promising targets. So yeah, as was said at the beginning, I'm not only use field studies in my research at DLR, but we also combine simulation experiments and lower Earth orbit experiments to push further the limits of life as we know it, and to look at the detectability of biosignatures using harsher and harsher conditions. Further experiments on the moon are coming with the going back to the moon exploration. And so this is all to help the exploration of Mars and the icy moon and support current and future missions. So yeah, I leave you with some poetic images of a crushed Martian or life after death. And I'm happy to take any questions, and thank you very much for your attention.